This video will give examples of continuity and its consequences. So we're going to look and see if this given function is continuous. I think the best way to analyze this is by drawing out a graph. Our point of interest is x equals 1, because that's where the function changes value. So for x less than 1, we just have a normal x squared function. And then when we get greater than 1, we end up with a negative x squared. So just from looking at this graph, we can tell that the function is not continuous. And we can say that the reason is that the limit as x approaches 1 does not exist. Now we have a given function with an unknown c, and we're going to have to find the c that will make this function continuous. Now if we look at the first portion of our function, we see that the top can be factored as x plus 2 times x minus 2. And we have on the bottom x minus 2. So we can essentially cross out these two that are the same and say that these two expressions are the same except at the point x equals 2, where this expression doesn't exist, but this one does. Okay, so what that means is that for x less than 2, we have a graph that looks just like the line x plus 2. So here's our point, x equals 2. And so we have this sort of a line. And so we can say that the limit as x approaches 2 from the left equals 4, because if we plug in 2 into this expression, we're going to get 4. Now the way to make this function continuous is we're going to have to make the limit as x approaches 2 from the right also equal 4. So the way to do that is if we plug in 2 into this expression, we're supposed to get 4. So c times 2 minus 2 equals 4, which gives 2c equals 6, or c equals 3. Now, if we have c equals 3, that gives us 3x minus 2 for the second portion of our function definition. And so if we want to graph that out, we can see that at the point x equals 2, our function takes on the value 4. So now we can get rid of the whole, and it just continues on with a slope of 3. Find the intervals for which f of x is continuous. So we've defined f of x as the natural log of x squared plus x minus 2. Now this function is continuous wherever it's defined. A natural log is defined when the inside of its expression is greater than 0. So that means our function is defined when x squared plus x minus 2 is greater than 0. So now all we have to do is find the x for which this is true. So we can easily factor this as x plus 2, x minus 1 greater than 0, which means we have a graph that crosses at negative 2 and 1, and it's pointed upwards. So from this we can see that our function is greater than 0 when x is less than negative 2 or x is greater than 1. So these are the intervals for which f of x is continuous. or in other words, from negative infinity to negative 2, and, which we can designate with a sort of U symbol, meaning union, from 1 to infinity. Now this is a pretty interesting question. Is it true that there must always exist two locations on opposite sides of the Earth at the same temperature? The way we're going to prove this is by using the intermediate value theorem. So I'm going to draw a really bad representation of the Earth. I'm just going to draw a big circle. And let's say we have a random point A. Then the point opposite that we'll say is A plus 180 degrees. So we're going to say that T of x is the temperature at point X, and the function that we're interested in, f of x, is equal to the difference in temperature between point X and the point directly opposite it. Now, let's plug in A into this equation and see what happens. What we get is that f of A equals the temperature at A minus the temperature at the point directly opposite it. And there are some possible values for this expression. Either f of A can equal 0, in which case we found the points that have the same temperature and are on opposite sides of the Earth, or case 2, f of A is less than 0, meaning that the temperature at this point is greater than the temperature at that point. In case 2, what we can now do is plug in the hotter point into our equation. So f of A plus 180 equals the temperature at that point minus the temperature at A. So if f of A was less than 0, then we know that f of A plus 180 must be greater than 0. And this makes sense because if this point is colder than this point, then you can also say that this point is hotter than this point. So what that means is we now have, here's our 2 points again, that this value is less than 0, and this value is greater than 0. And so now, by the intermediate value theorem, I can choose a number between f of A and f of A plus 180, and so I'll just choose my number to equal 0. There must be some c between these 2 points such that f of c equals 0. And the meaning of f of c equals 0 is that the temperature at C minus the temperature at the point opposite it equals 0, or that they're at the same temperature. There is a third case. If f of A is greater than 0, then you can go through the exact same reasoning and say that f at the point opposite it is less than 0, and again apply the intermediate value theorem to show that there must exist a point between them where the difference in temperature is 0.